Welcome to The Explainer. Today, we're going to crack open what people call the black box of artificial intelligence. Using some key ideas from the book Math and Architectures of Deep Learning, we're going to completely change how you see AI by turning these complex, scary equations into simple, intuitive pictures. All right, let's get into it.
Let's start with this quote because it is so key to everything we're about to talk about. Look, the goal here isn't about memorizing a bunch of formulas. It's about building a mental picture, this geometric intuition, for how deep learning really, truly works.
For a lot of people, AI and deep learning can feel, well, like some kind of black magic, right? You feed some data in one side, an answer pops out the other. But what's actually happening inside that box? It's a total mystery.
But what the authors of our source materials say is, it really doesn't have to be this way. They believe that if you can understand the geometry behind these models, you can go from just using AI to actually understanding it.
So this brings us to a really fundamental question, one a lot of people ask when they first get into deep learning. If the tools work so well right out of the box, do we really need to bother with all the math underneath?
And this is where it gets really interesting, because there's a trade-off, right? Using a pre-built AI tool can get you fast results, no question. But the book makes a great point. Without understanding the math, you're kind of stuck. You're locked into just using the tool as it was intended. You can't see the big ideas, the abstractions, that let you innovate, or fix things when they break, or even come up with something totally new.
So, if the math is necessary, what's the best way to tackle it? And the book's answer? It's super clear. Forget about memorizing abstract formulas. It's all about seeing the geometry. So the whole idea, the core philosophy, is to build what they call geometric intuition. What does that mean? It means learning to see machine learning problems visually. So instead of just seeing a bunch of equations, you start seeing points and lines and these crazy high-dimensional surfaces that are separating different kinds of data. And by thinking in this visual way, we can build those powerful abstractions we need to really get the how and the why behind these models. Let's bring this down to earth with a really simple example. Okay, let's imagine a super simple problem. We want to build a model that acts like a cat's brain when it's trying to decide if an object is a threat or not.
So to do this, we've got to define some features for any given object. Let's just keep it really simple and use only two. How hard is it and how sharp is it? So a rock is hard and sharp, that's a threat. But a ball of yarn, that's soft and dull, it's safe.
And this is where the magic really happens. All of a sudden, this classification problem becomes a geometry problem. Every single object from our table can be just plotted as a single dot on a simple 2D graph, right? We put hardness on one axis and sharpness on the other.
Now, the book explains that solving this is basically a three-step process. First up, we pick a model architecture. And for this, the simplest thing is just a straight line. Then we do the training. We show the model our data and let it figure out the best possible line to separate the threats from the non-threats. And finally, we use that line to make predictions on new things it's never seen before.
And boom! That right there, that's the core idea. The machine learning model is nothing more than a geometric separator. We've turned what seems like a complex decision into a super simple geometry problem. Just find the dividing line. And that line has a name. It's called a decision boundary.
Okay, that's a cool little example, but how in the world does this simple cat brain with a single line scale up to the incredibly powerful AI models we have today that can do things like recognize faces or even drive cars? Just remember, our little cat model was working in this super simple, two-dimensional world, just hardness and sharpness. That's it. But real-world networks, things like LeNet, VGG, or ResNet, they are way, way more complex. Instead of just two features, their input could be every single pixel in an image. That pushes them into spaces with thousands or even millions of dimensions. But here's the absolute key, the crucial point. Even these gigantic, complex networks, they're built on the exact same fundamental principle. They are still just learning a geometric separator. Okay, so it's not a simple line anymore. It's a really complex, high-dimensional surface, what you'd call a hyperplane, that separates all the points that represent cars from all the points that represent giraffes. So let's bring this all home. What does this new way of looking at things, this geometric perspective, actually give us? How does it help us finally open that black box?
By really focusing on this geometric intuition, we're not just learning how to use a tool anymore. We're actually starting to get why it works.
We're beginning to see the big, powerful ideas, the abstractions, that make it all possible in the first place.
So what's the big takeaway here? Number one, deep learning isn't magic, it's just geometry in a lot of dimensions. Number two, those simple geometric ideas from our cat example, they are the very same ideas that scale up to solve these huge real-world problems. And maybe most important of all, when you start thinking visually about AI, that's when you can go from just being a user to being a creator.
And that kind of leaves us with a final thought to chew on. If even the most complex problems in AI are really, at their core, just about finding the right shape to separate points in space, what new challenges could you tackle by starting to look for their hidden geometry?